So it's great to share some of the work that I've been doing with collaborators in physics and in math. For the past 7 years, I've been working sort of at the intersection between math and theoretical particle physics. And yeah, I had the opportunity to develop some new mathematics to explain and explore what we've been seeing. And today I'll just report on what we found and have some new results in geometric combinatorics along the way. Okay, so yeah, so let's begin. So the physical framework, we're going to take some d, usually bigger than or equal to 4, and equip r to the d with a Lorentzian signature bilinear form. We'll take n momentum vectors, p1 through pn in Rd, such that they have sum 0 and that they have norm squared equal to 0. That's the massless condition. We're going to define Mandelstam invariance, Sij, to be the square of the sum of pi and pj.
Does Lorentzian mean 1 comma d minus 1 or d minus 1 comma 1?
One positive eigenvalue. It doesn't really matter for physical purposes.
And every time you will say norm and so on, it will be always with respect to that.
Yes. I probably won't say that again. Yes. Standard physical notation. Yes. 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 Okay. Okay. So with this setup, let's look at a 2-particle amplitude in the phi cube theory. And in that case, we have 2 planar cubic trees that embed in a disk, where the disk is oriented cyclically, 1, 2, 3, 4, around the boundary. Okay, so here we have the 2 Feynman diagrams. Feynman diagram, you put an orientation on each edge, and you attach to each edge a decoration, a momentum vector, and you require that the sum of the momenta has to vanish at each vertex. That's called momentum conservation. So from this, the Feynman rules say we're going to evaluate this Feynman diagram, and we get S12, which is P1 plus P2 squared. Okay, this is well defined due to momentum conservation. This is also equal to P3 plus P4 squared, because we have the sum of the four guys is 0.
Why are there only 2 of these things?
Because those are the only, there is a third one. The third one does not embed into the disk without a crossing.
And why can't I have like P1 plus P4 in the middle?
Because we do in this case, but it's equal to P1.
I see.
When you reverse arrow, so the square is the same.
Was this cyclic orientation on the 4?
On the 4 legs, external legs, exactly. So imagine there's a disk going around like that. Or like that.
So you're going to be focusing on the planar graphs, right?
Yes, yes. At least for now. In the next slide, we'll have the third guy as well. So Feynman gave us a simple recipe to compute scattering amplitudes in perturbation theory. In particular, one of the simplest theories, the cubic scalar amplitude. So the recipe is you write down all trivalent directed graphs with n external edges and internal edges, say labeled E sub int. Then each edge E is decorated with a momentum vector. You must have momentum conservation at each vertex. Feynman rules say the following. We take a Feynman diagram as we had before. For each internal edge, we take a product over all the internal edges, and to each internal edge, we attach the squared sum of the momentum flowing through that edge. Okay, and then we sum over all tree-level Feynman diagrams. So that's the sum over all cubic trees embedded in a disk with n external leaves. and external legs. Okay, so the 4-particle full phi cubed amplitude, when we allow crossing, we allow the third diagram. Okay, it's that. And here we have that 1, 3, which corresponds to the non-planar pole with respect to the cyclic order. Okay. So the main player in this talk is the moduli space M0n, which we just heard about. Over the complex numbers, well, points in the space can be represented by 2 by n matrices, such as this representation, which will be pretty standard for us. Fixed 3 points, 0, 1, and infinity, and then you have n minus 3 degrees of freedom. And the real configuration space decomposes into some tiles due to the as follows. According to the signs of the 2 by 2 minors in this matrix. Okay, and in this case, when you order the points increasingly from 1 to n minus 3, and you compute all the 2 by 2 minors, you can see that they're all positive. All 2 by 2 minors are positive. So the structure of such decompositions, such as this one, of course, it fits into a general framework of the theory of oriented matroids. And so that will play a role in this talk as well. That'll play an important role.
What is a planar?
By tile simplex. In this case, a simplex. Tile is using tile to be consistent with the structure at higher k when the topology is just a semi-algebraic set.
You just mean a connected component.
A connected component, yes.
So we fix signs of Pij's and we ask which satisfy this our sign pattern, and that's an open tile.
Yes, exactly. And in this case, for M0n, the real M0n, yeah, they're all n minus 3 dimensional simple C's. Yeah.
So what does simplex mean to you? Actually, not a simplex. It's not a simplex, but.
Yeah.
But if you look at the next one. It's not bounded. It's not compacted.
Yeah, so that's kind of why I used the word tiles in the previous section. Okay, so if we fix an affine chart as a projective frame, as we saw in the previous slide, for n equals 5, M05 here is the complement, these 1, 2, 3, 4, 5 lines. Now we have 12 connected components. Among these, 2 of these are bounded, simplices, triangles. And in total, yeah, in total there are 12. Okay, so roadmap for the talk. So we saw the Feynman diagram prescription for computing scattering amplitudes, but also in 2013 to 2014, 3 physicists, Cachazo, Hay, and Yuan, introduced a novel formula for computing these amplitudes. And this formula is closely related, very closely related to the moduli space M0n. And then in part 2 of the first item 2 of the first part 1, then we'll use techniques from oriented matroids to discuss some certain identities among amplitudes and identities among rational functions, which you find here.
So is this work of Cachazo just for cubic or more general?
Yeah, so the basic theory which we're talking about today is for the cubic scalar, and they formulated it, in fact, for many other quantum field theories, yes.
And do they go beyond the tree level or is it still all at tree level?
There is work, there indeed in one loop, there is a formulation in one loop, yes. And there's work on two loops.
And these involve the matroid structure too, or do you have to go beyond that?
Yeah, you kind of have to go beyond it, yes. Yes. I mean, yeah. And yeah, and in the second part of the talk, we'll discuss a generalization called generalized Biadjoint scalar amplitudes, or Biadjoint is kind of a decoration you put on phi cubes. So you consider these generalized cubic scalar amplitudes, and then we'll look at the combinatorics and the tropical geometry of amplitudes, which allows you to understand their fine structure. So some notation. In physics, you have a fundamental object. The fundamental object is called the kinematic space. And it's the space of symmetric matrices such that every row and every column sums to 0. That's due to momentum conservation, where the momenta sum to 0. A priori, you could take these to be just complex parameters. Then amplitudes make sense there too. Ultimately, for physical applications, you want them to be specialized to Lorentzian inner products. So the Grassmannian GKN, space of K by N matrices, modulo row operations. G circ Kn, will assume that all maximal minors are non-zero. XKN, take the generic subset of GKN and then mod out by independent scaling on each column. So take a K by N matrix, and you're allowed to multiply each column by a complex number. And so that's equivalently, that's the configuration space or moduli space consisting of generic configurations of endpoints in pk minus 1. So note the notation, x2n, you recover m0n. So one important feature is that genericity for the moduli space does not mean pairwise distinct. It's a stronger condition. It says that no k points can be coplanar. And here I've given one choice of a projective frame in this case for x36, and the dots go on for x3n. Okay, so we saw that M0n is tiled by 12 open cells, and some of them are obviously simplices. 2 of them are. Now we define the so-called Parke-Taylor factor to be 1 over the product of the consecutive, the cyclically consecutive minors with respect to that cyclic order. Okay, so P alpha 1, P alpha 2 is the determinant of the maximal minor, maximal 2 by 2 minor with columns I and j, alpha I, alpha 1, and alpha 2. So for example, for M05, to the 2 bounded tiles, we have the following 2 rational functions, the 2 Parke-Taylor factors. And you can see that, you can see is that x1, you get all the bounded things. So the Parke-Taylor factor has a singularity, a manifest singularity on each of the 3 facets.
So from now on, M0n, you mean like real points?
Yes.
I couldn't quite tell, what are you labeling?
What are we?
I mean, I can't tell from the picture, I couldn't, what are you labeling? Like, what is P1, 2, 3, 4, 5 attached to?
P1, 2, 3, 4, 5 is a rational function which has singularities, logarithmic singularities on the boundaries of that triangle.
It's associated to the triangle.
Yes.
And
similarly, when we swap 2 and 3, then we get the thing with logarithmic singularities on the boundaries of the lower triangle.
And is that just you choose a base thing? Did you just choose that the first triangle to be the base and then everything else from it, or is there some other way I should?
I think the sequence of numbers is so that points are increased in order. So there's a real point, you can order them, they labeled, and this is
Yeah,
so it means that P1 is less than P3, less than P2, less than P4, less than P5. That's given.
X's, yes.
Oh, X, yes, okay, yeah.
Exactly. So, yeah, so all minors, for this particular, this is characterized by an increasing sequence of X's. And it's characterized by, in other terms, it's the torus quotient of the part of the Grassmannian where all minors are positive.
So this is the PT in the picture is different from the PT that you define above.
It's the same. I just wanted to fit in.
The
But
second one has one.
upstairs, this has 5 terms, 5 minors. Some are 1.
Some are one, yes.
Out of 12 things in there by 12 different permutations, 1, 2, 3, 4, 5.
They're all related by permutations of 1, 2, 3, 4, 5, yes.
So which 12 permutations?
So in M0N, due to the group PGL2, the same chamber is determined by both, it's invariant under cyclic rotations of the ordering and the dihedral flip of the ordering. So you can see that from the action of PGL2. Yeah, and you cannot, I should say, you cannot see it manifestly from this formula, but there is a statement about torus invariance, and you'll see that this actually has singularities on higher codimension faces after the blow up as well. We'll see that as well, because this is a function ultimately on M05. See that. Okay, the first ingredient in the CHY formula, the so-called scattering potential. We have the following kinds of hyperplanes: xj, xj minus 1, and xi minus xj. Okay, we take the scattering potential S, we take the logarithm of xj multiplied by the corresponding Mandelstam invariant, and you sum over all possibilities. Note that this is actually a sum over all n choose 2, but some of the logarithms are equal to 0. So for generic values of the Mandelstam invariance, CHY found that the scattering potential has n minus 3 factorial critical points, and that when they are real, then they are in the bounded components. For a mathematical proof, you could see, for example, Barchenko's work.
Does he use this language?
Varchenko?
Yeah.
No. Not the scattering equations, no. He uses
Language does he use?
Generic hyperplane arrangement. Just he shows that the number of critical points of such a function is equal to n minus 3 factorial when the parameters are generic.
But
The
not.
hyperplane arrangement is not generic. Parameters are.
Yes, sorry, yeah, hyperplane, yeah, exactly.
So this is the maximum likelihood degree.
Exactly,
Of
which is,
of the braid arrangement.
which is, of course, well known to, we've looked at that many times, yes. Okay, so the second ingredient is the following formula. We take product of the two Parke-Taylor factors associated to the cyclic orders alpha and beta, and we sum over all critical points after dividing by the determinant of the Hessian matrix. Okay.
What is that?
M is notation, physics, this M? Physicist notation for the amplitude. So that stands for, in full language, Biadjoint scalar partial amplitude. So M is defined, you can take it to be defined by that formula.
So this slide for us is just saying, this is an interesting, the right-hand side is interesting. Is that
Yes,
what we
that's
should-
right.
what you want?
And in physics, it's important to have these cyclic orders in the interior. So a priori, there is one partial amplitude for each pair of cyclic orders. And And yeah, and it's given by CHY's contribution was that it can be evaluated by that formula. It's also evaluated by an explicit Feynman diagrams summation, as we saw previously. So the magic of this formula is that this evaluates to the same function of Mandel-Stem invariance that you would get by summing over Feynman diagrams.
It's like a Deutschmann-Heckman type of thing.
For
Something over critical points in the hashing.
Oh, I think so, yeah. Okay, I haven't thought about that, but yeah, sounds right. Yeah.
So we sum up over those critical points, and we mean that we evaluate those functions that we get at those critical
Yes,
points.
yes, there should be an evaluation C there. So just note for the experts, a bit of complex algebraic geometry is that just you can rewrite this as a multivariate residue theorem. You can read in Griffiths and Harris in this way. Take a polydisk about the derivatives of the scattering potential. You divide by the product of all of the first derivatives and divide by 2 pi to the 1 over 2 pi I and to the n minus 3. And that's just another way to write the same thing by the global residue theorem.
Can you say maybe 2 or 3 words on the physical interpretation of this formula upstairs?
The formula on the right-hand side?
The M has something to do with the scattering amplitude, right?
Yes, exactly. So for each fixed alpha and beta that does not have an interpretation in the scattering amplitude, the physical interpretation you get by summing over all cyclic orders, alpha and beta. In that case, when you sum over all cyclic orders in alpha and beta, then you recover the full phi cubed amplitude that is permutation invariant. That had that extra term 1 over S13 in it. So just a quick computation. Okay, so here's for n equals 4, the n equals 4 scattering potential. S12 times log of x, S23 times log 1 minus x. We compute the ML degree is 1. We compute, and additionally, we have the Parke-Taylor factor on 4 elements, x minus 1 times x. So the ML degree is 1. And the one critical point is given by S12 divided by S12 plus S23. And so having done that calculation, we have to, the summation from the previous side is very nice. It has 4 minus 1 factorial critical points. And so we get exactly, if you plug these numbers in, I invite you to do that for yourself. You get the numbers from the expression from the first couple slides. Okay, so that kind of provides the full context for the talk, motivation, and so now we'll start to dig into some more of the mathematical structures. So there's something called the set of all poles of the cubic scalar amplitude, they're in bijection with subsets of 1 through n of size 2 to n minus 2, in bijection with the divisors, times 0, 1. So it's inconvenient when we're talking about Feynman diagrams in a Feynman diagrams in a disk with a fixed cyclic order on the boundary, 1, 2, 3 up to n, to introduce the special notation xij, where I and j is the chord between the points I and j in the polygon. So it's for each chord of ij of an n-gon. So you can calculate explicitly, and this is important, you can calculate explicitly from this formula First, that the n choose 2 minus n variables xij are linearly independent. There are n choose 2 minus n, the minus n arises, that's an artifact of momentum conservation. It says that whenever I and j are cyclically adjacent, then that expression is 0. Okay, because pj Sii is equal to 0. So these collectively, these xij's are called the planar basis.
This is thinking of them as polynomial. What's literally like the vector spaces where?
Yeah, the planar basis for the space of linear functions.
Sorry, I thought that SABs were numbers, just.
No, I thought they were, yeah.
They are coordinates on the kinematic space. So we're taking them, so at the beginning we said we have n momentum vectors, but those momentum vectors are allowed to vary.
Okay.
Yeah, so you can think of these as functions on the kinematic space, which we introduced before, K2n.
We just, sorry, so your vector space is just something with basis AB or IG.
It's spanned by the SABs, and it has a codimension, it's a codimension n subspace of it. It's subject to the n momentum conservation relations. So if we remember, we wrote our scattering potential as the sum over all ij of logarithm of the determinant Pij times the Mandel-Stem invariant Sij. Well, you can rewrite this. First, group the log, bring the log out front, and then organize the xij's as the exponents. Then it turns out that the factors, the bases here are these cross ratios, these very nice cross ratios. Read that Pij, Pi plus 1, j plus 1, Pi comma j plus 1, Pi plus 1 comma j.
What's in ... 1, 3, 1, 4, and
Oh, all of them, all n choose 2 minus n chords.
which n is not the thing there?
He's thinking of the actual proper chords of an n-con, so not,
So
not the adjacent ones.
The set of all
Edges.
xij for ij a chord, it's not a boundary. Okay, so recall that there are like n minus 3 factorial critical points. And that's super hard to compute for n reasonably large. So you'd like to still get insight into your scattering amplitudes. And it turns out you can do that by restricting to subspaces of the kinematic space where some of the Mandel-Stem invariants are 0. You'll see that the number of critical points drops, and the amplitude which is being computed, it becomes a little bit simpler. So something called minimal kinematics. We're going to take new variables alpha 1 through alpha n minus 2. They're just complex variables, and introduce these set of constraints on the x's. So xij is the sum of alpha 1 through alpha j minus 2. The effect is that you set to 0 a whole lot of the Mandel-Stem invariants. In that case, the scattering potential now simplifies extremely. And this is maybe the first example, the first standard example of an ML degree 1 log likelihood function. And so on M0n, it gives rise to this parameterization. So you can choose the gauge such that this is exactly the unique critical point. So when you make this specialization, it turns out that there's exactly one critical point in M0n, and it has this form. So you can see it just continues alpha 1 plus alpha 2 plus alpha 3 plus alpha 4, etc., all the way on over. Moreover, when the alphas are real and positive, then all of the minors are positive, and you're in the standard tile.
You really mean CP2 embedded at M05?
Yeah.
Well, let's see, what do I mean? So if over the complex numbers, yeah, so alpha 1, alpha 2, alpha 3 are coordinates on CP2. Yeah, and you can choose like usually you choose a chart where alpha 1 is equal to 1. So it actually, it is.
A big part of the complaint was you don't, maybe using the torus of CP2.
Oh, I see. Oh, perhaps.
Torus with distinct entries or.
Yes, thank you. Yes, yeah, no, thank you. Yes.
I mean, just like complement of 6 lines in P2 is M05. I think that's what it's saying.
Okay, so here is what the amplitude for the planar phi cube theory looks like in terms of the x basis. We take a sum over all of the triangulations of a polygon, of a 5-gon. If we specialize alpha 1 through alpha n minus, if we specialize the x's in this way, well, then you get this nice simplification of the amplitude. So it looks like something like a simplex, the boundary of a simplex, the cone over a simplex triangle. And the figure at the bottom, it represents the triangles which are related by flip moves. So pairs of chords and pairs of chords, triangulations are related by a flip move, and that's how it's organized. So let's try another approach. So in general, the amplitude m sub n, I'm just taking an abbreviation, is the sum over all triangulations of an n-gon, where you take a product of the chords, inverse of the product of xij, where as I and j run over the chords of that triangulation. Of course, there are Catalan many of these triangulations, and that gives you the amplitude. And the proposition was that on minimal kinematics, you actually get this beautiful formula. So when you take, when you take this expression and restrict the x's to the sums of the alphas, then it simplifies to this expression. And the idea of there's a combinatorial proof in terms of the triangulation of a certain polytope. A polytope has been studied by Postnikov and Gelfand and Graev. It's called the root polytope. Anyway, that's what it looks like here. In the next slide, I'll show you the explicit combinatorial interpretation for the 5 simplices that you see here, right? So each simplex here, each tetrahedron corresponds to exactly one of the Feynman diagrams, one of the products of the x's. So here is their picture. There's a nice bijection between Feynman diagrams or simplices in the triangulation of the root polytope and these trees with arcs. So the procedure is in general that you take all arc diagrams like this, and each arc diagram like this is associated to alternating trees, I think they call them, and each one of those is associated to a simplex in the triangulation of this root polytope. So that's just the idea for the proof, that you reduce this amplitude computation to the computation of the triangulation of the root polytope. Yeah. Okay. Yeah.
So for M06, the dimensional blow up would be 4-dimensional, or?
Yes, so it's actually a cone over. I mean, so There, in the root polytope, there's always it always extends from the origin out. So there is an extra dimension, so it's a cone over the boundary.
It's also the theory of Francis Brown, who looks at cross ratios.
Yeah, exactly.
Looking at an n-gon and certain.
That's like throughout this talk, it's a substrate for this, yes, exactly.
But is there a combinatorial dictionary between this roots polytope subdivisions and this combinatorial scheme of Francis Brown?
Well, let's see. Well, if we want to connect to Francis Brown's work, his dihedral cross ratios correspond to they're exactly the U's, I think same notation, the Uij's, which are ratios of P's, right?
Yep.
And I think he uses delta ij or something, and those become the X's. Those become the X.
Yeah.
Xij's.
Precisely. But does that correspond to this polytope subdivision?
Yeah, so this is the what's the direct relation? Well, another name for this is the dual isosahedron. I guess I'm not sure how to answer your question. Okay. Okay, so tiling moduli spaces. Oh boy, running behind. Okay, tiling moduli spaces. So components of the real Grassmannian are distinguished by vectors of signs of the Puka coordinates. These are axiomatized by oriented matroids. And the 12 components of M05 or X25 are distinguished by the following 12 sign patterns among the U variables. And apologies for the notation. This is U1 here is U1 is P24. This is U24, U35, and so on. But the important point is that the sign patterns are all the admissible 12 guys. And you can choose a chart and realize them. And these are exactly the realizable sign patterns. And the 12 rank 2 oriented matroids on 5 elements. Modulo torus scaling, modulo reorientation it's called. So to each tile, we associate a differential form with logarithmic singularities on its facets. Yes, remember we had the triangle, and the Parke-Taylor factor had manifest singularities on each of the facets. What I didn't say was that there was also a dx1 wedge dx2 associated to it. Okay, but if you write it using that way, you can see that it's actually a wedge of d logs of cross ratios. It's like d log of cross ratio 1 times d log of cross ratio 2, etc. The point is that if you take your Parke-Taylor factors and you shuffle 1 through 2, 3, 4, 5, you get an identity. So these 4 guys sum to 0. In physics, that is called the U1 decoupling identity from a certain property of particles.
You want symmetry in this problem or?
So in the full Biadjoint scalar, you would introduce color factors that are traces of products of matrices, and U1 decoupling would correspond to when one of your matrices is no longer generic, but commutes with all the others. Right. Apologies for.
Is 2, 3, 4, 5, 1 not one of the terms because it's like a cyclic permutation of 1, 2, 3, 4, 5.
Yeah, exactly.
Which areas would this be in your picture?
Oh, I didn't. That would be a good thing to include next time. Yes. 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 Yeah. So thank you. Yeah, it's a good point. Okay, so I want to go now beyond M0n to starting with x36 to xkn, but we'll look at x36, 6 lines in projective plane.
So actually, so it would be, just let's with the
Sure.
slide. So are the U coordinates, are they just getting rid of the dihedral symmetry? Or why do we pass to the U coordinates?
It's a convenient system of cross ratio, the convenient coordinate system, yeah. Especially adapted to the positive part where all the plukers are positive. So when all the plukers are positive, then each U takes a value between 0 and 1. So that's why it's shown.
As a cross ratio, it's not products, it's just like. So that generates a coordinate string of.
Yeah, I don't think I'm good for it.
Okay, so now we're getting into some really more recent work due to in collaboration with starting in 2019. This is with two physicists here, Alfredo and Sebastian, over in the School of Natural Sciences, and then and Freddie Cacciazzo at Perimeter, and Yang Zhang, who's also at Perimeter now. Okay, so what it turns out is, while there are n-1 factorial over 2 different tiles, connected components in M0n, and moreover, they're all related by relabeling. They're related under the action of the symmetric group. That no longer holds in XKN. There are a lot of different permutation types. There's a lot of topologically different tiles. And so, in fact, just as in M0n, when you compactify, each of these tiles blows up to an isosahedron. In this case, each of the connected components blows up to a polytope. It's actually a polytope, and those polytopes have those 16, 14, 14, and 15 facets, and so on. So they are 4-dimensional polytopes. Every tile in X36, the real X36, is a polytope with one of these guys. It's a pretty nice structure. Moreover, each of these tiles comes equipped with a differential form, like a Parke-Taylor factor. And via the CGM formula, which I'll introduce shortly, it's direct generalization of CHY to XKN from M0n. From each line arrangement, you're going to construct a differential form, or in this case, the coefficient of the differential form. Okay, so these are the 4 kinds of analogs of Parke-Taylor factors. So here are up to relabeling, here are the 4 different types of, they're representative, one representative from one of the permutation types of each tile. So here we see here we see exactly one hexagon, one big hexagon, and it's bounded by 6 triangles. Okay, those 6 triangles, each of those triangles gets a factor of a Pluker coordinate in the denominator, right? So we go to the boundary of this tile when we slide one of the lines a little bit, and and one of the triangles shrinks to a point. So the simple boundaries in X36 are characterized by shrinkings of triangles to points. So each of these forms, say this one, has a singularity when that guy sneaks up there and crosses, when 3 sneaks up and intersects 4 and 2 like that. Okay, and similarly, we can do triangle moves to take line 1 and slide it over and replace it with replace this triangle like that. We do a little triangle flip here, and we can do it again and again. And although you cannot see it, there are triangles wrapping around infinity here, and you get 6, 6, 7, and 10 triangles in the different arrangements. Okay, so you remember we had this this decoupling identity for M0n, for Parke-Taylor factors on M0n. There's P1234 plus P21345. Like that. Well, you'd like to find analogs of such identities for x36, for xkn. Right, so you take the generic line arrangement of n-1 projective lines. Now come along with a new generic line in all possible ways. So each one, when you put it in generically, each one of those corresponds to a point in a tile in x36. So we start with a point in x35, we come along with a new guy, we get a point in x36, and we do this in all possible ways. Well, it turns out we get 31 possible tiles. In the language of oriented matroids, it says that there are 31 one-element extensions of an oriented matroid in n equals 5. So these identities are no longer irreducible, right? So we had like P12345, 21345.
That was realizable. But all the extensions.
Yes. All of them are realizable in this case. And so, right. So on M0n, you get the decoupling identity is a sum of Parke-Taylor factors which sum to 0. Set of Parke-Taylor factors which sum to 0. There are no sub-identities among them. Like you can't take a subset of 3 guys, they don't sum to 0 at all. No sub-identities. But it turns out that there are a lot of different sub-identities among these 31 guys which you get. So the challenge in our paper was to find which are the irreducible sub-identities, right? And so this is just this is one of them, and you can contrast it with the decoupling identity you see here. So a priori, the signs, you have to figure out the signs. The signs are fixed such that your differential forms cancel on the common boundary of the tile. And you take the sum, the common boundary has to cancel. Yeah. So, okay. So part 2, I'm very far behind. But okay, so do it again. Okay, so generalized Biadjoint scalar amplitudes and combinatorics and tropical geometry of amplitudes. Okay, so how did we get to this point? Well, there's Grassmannian duality, which says that G2n, GKn is isomorphic to the same as Gn minus k comma n. So the same identity, this descends to an identity on xkn's. And so you see that there are 2 different realizations of the CHY formula. One on M0n and one on its dual. Okay, so we like to say that, well, they could have in 2013, they kind of missed the opportunity to ask what comes in between there, you know, right? It's a pretty natural thing, you know, what kind of amplitudes do you, what kind of objects do you get by working in between? So in 2019, like 6 years later, with Alfredo and Sebastian, we generalized the CHY integral to xkn, filling in the gap. And then we discovered that our formulas actually appeared in the math literature. In particular, they appeared in the work of Bernd Sternfels and David Spire on the tropical Grassmannian. So in that work, they computed so the tropical Grassmannian is a certain, it's a certain collection of cones, certain collection of 4-dimensional cones for x for 3 comma 6. And we discovered that a direct correspondence between the objects we were calculating with Feynman diagrams and the maximal cones in that tropical Grassmannian. So in other words, to summarize, connection to geometric combinatorics quickly materialized. Okay, so we have to define the scattering equations for xkn. So here, the scattering potential for 3 comma n is following, have a log of the 3 by 3 minor, multiply it by generalized Mandel-Stem invariant. We'll assume that these are just complex parameters. We're not going to make any sort of specialization to the momentum vectors. So just take them to be complex numbers. You have to satisfy some identities in order to make it well-defined in x3n. Right, so if you scale like the first column by number t, well, the result better be independent of that scaling. So that means that you get exactly n linear relations among the SABCs. Anyway, once you do that, it is well defined in x3n, and you can fix this. You can let P be a maximal minor of that matrix. So there's a statement about the SABCs. Now the natural thing to do, remember the Parke-Taylor factor is 1 over the product of the cyclically consecutive minors. Natural thing to do is take 1 over the product of the cyclically consecutive 3 by 3 minors. Right, that makes sense. And you can define then in the exact same way a sum over all of the critical points of your log likelihood function. Take 1 over the determinant of the Hessian matrix. Take the product of the 2 Parke-Taylor factors associated to those cyclic orders. Evaluate at the critical point. Evaluate. And yeah, that was our definition. That was our defining formula for this amplitude. And then we saw, well, look, we started to find maximal cones among the tropical Grassmannian from this formula. So here's the actual formula. Instead of things like 1 over S12 plus 1 over S23, well, you have these more exotic things. So yeah, product of some S's, product of some other linear functions. And for the experts, they might recognize this coming from the tropical Grassmannian G36. This corresponds to the bipyramidahedron. The bipyramid. Anyway, there's in one of the maximal cones in that is a bipyramid, and that's related to this guy. So they satisfy some very interesting non-trivial linear relations among the poles. For example, the 2 R factors in the numerator, you take their sum, they're equal to the complementary 3 poles. And so that's a novel feature from phi cubed, from the planar phi cubed or phi cubed in general. Now we also noticed that there's a new kind of Feynman diagram which you do not see from this formula. Okay, so these are both products of cyclically consecutive minors. You would not get out this contribution to the amplitude. The reason is that, anyway, S246 is not cyclically consecutive. Okay, so that's the mystery that was presented to us, and we went about to explore the combinatorics. Okay, so on the note of combinatorics, we had our planar basis of xij's. Well, we'd like to generalize that to some notion of x sub a k element subset, such that each one of them is a pole of the amplitude, characterizes the pole of the amplitude, and there should be some analog of the crossing chords construction, right? So here, for the 4-point planar phi cubed, well, the amplitude is encoded by the 2 triangulations of a square you cannot have 1 over x 1 3 times x 2 4 in that language because the two chords would cross. So we should have some notion of that among some notion of x with a k element subscript. Okay, so the way to do that required a kind of novel construction. For that, I need to mention a polytope, which is well known, very well known in geometric combinatorics, the hypersimplex. It's defined to be the convex hull of all some k-fold sums of indicator vectors over any k element subset. Take that, take the set of all those, and take the convex hull. So that's the notion of a hypersimplex. Now the breakthrough happened when I did that. So combination guessing this formula, I'll explain what all this means. It's and you find that modulo momentum conservation, this combinatorially constructed coefficients are equivalent to S12. They're equivalent to the planar propagators, the planar poles of the amplitude. Okay, so I just want to sketch the rule. This is in terms of a certain directed distance function. It says you start down here at the vertex 0, 1, 0, 1, or E24, E2 plus E4, and you walk in steps of E1 minus E2, E2 minus E3, E3 minus E4, and E4 minus E1. So like here you get a walk length 1, walk length 1, walk length 2. And so you put the corresponding coefficients, the corresponding walk lengths in the summation. So the general definition is it's a directed distance function on the one skeleton of the hypersimplex. You take the minimal walk from EI to EJ in steps of these cyclically consecutive routes. And that's the definition. This is what works for the planar basis, the new planar basis. So remember we had that the planar basis of, in the case k equals 2 for M0n was, it satisfies, it is a basis. And moreover, when the k element subset is a cyclic interval here, it vanishes. That says that says it is in the lineality space of some vector space of the tropical Grassmannian in another language. But yeah, so we're going to introduce a very special basis of weight vectors. So we know that the xij's are a basis. They're linearly independent and they span the space of dimension r to the n choose k minus n. They're linearly independent and they satisfy a certain very important family of identities. Okay, you let H sub j range over all j element subsets which are not cyclic intervals. And they satisfy these important family of relations. And you'll immediately recognize that these are the positive tropical Plucker relations. Okay, so the space of all elements of r to the n choose k that satisfies these relations is a very rich object, very interesting object called the positive tropical Grassmannian. It's a polyhedral fan consisting of realizable tropical Plucker vectors. And what do we have next? Yeah, so that's so in the we'll need an analog of the triangulation condition. What is the analog among the x sub j's, capital J, for the crossing condition for these guys? So that's where we're going next. We want to develop an analog of the crossing chords condition. Okay, maybe. How are we doing on time? Can I take a bit longer?
Yeah.
Okay, I'll have to. Okay. Let me skip to the conclusions here. Anyway, so the main result is following. the analog of the chord, crossing chord condition is the following.
Also, there's another topic.
HI and HJ are compatible and satisfy the tropical Plucker relations if and only if their difference alternates sign exactly twice with respect to the cyclic order 1, 2, 3, or up to n. So that's the analog of the chord crossing condition. Idea of the proof. Well, anyway, you have to restrict to the octahedral faces, and you check whether each octahedral face is induced on it a matrix subdivision or not. You don't want any new edges. So that's the main result, and we skip here to the summary and directions in future work. So critical points of the scattering potential, we looked at minimal kinematics to peek into the structure of amplitudes. And ask, are there broader implications for scattering amplitudes? What does minimal kinematics mean for the tropical Grassmannian? It's some sort of projection. We're introducing some linear relations among the x's, but some sort of projection of the tropical Grassmannian. We looked at decoupling identities through the lens of configuration spaces. There's some geometric combinatorics in terms of oriented matroids. In physics, you'd like some additional structure here to explain how these decoupling identities, what they mean physically. So there's some progress on that. There's some progress in terms of a Lie theoretic realization. More investigation is needed. Second, the penultimate question, what are generalized Biadjoint scalar amplitudes? What are they computing? What do they mean? And just maybe they will help us answer a deeper question. What are scattering amplitudes, period? So how do you define them intrinsically? What are the necessary and sufficient conditions for such a function to be a scattering amplitude coming from a quantum field theory? Thanks a lot.
Questions for Nick?
Yeah.
One, I didn't follow the last part of that. You had answers for that, but if next cross residues, yes, we seems. Do you understand now combinatorial description of generators and relations for that?
Oh, for the analog of the cross ratios? Yes, it's very nice. There are some, I didn't get to talk about the analogs that I use here, but they are very nice.
Great.
Yes.
Okay, let's thank Nick.